So we have physics Ph.D. qualifying exam practice problem number 18 in statistical mechanics domain. So, sorry, let's begin. Consider a ferromagnet near its critical temperature described by the free energy functional F of T comma M equals F naught plus A quantity T minus T sub C M squared plus B M to the fourth plus C M to the sixth with AB greater than 0 and C greater than 0. Part A, determine the equilibrium magnetization as a function of temperature. Okay, so let's do part A. This is a phase transition and Landau theory problem. So for part A, equilibrium magnetization, our free energy, F equals F naught plus A times the quantity T minus T sub C, M squared plus B M to the fourth plus C M to the sixth, with A, B, C greater than 0. We're going to let tau equal T minus T sub C. The equilibrium requires this partial derivative of F with respect to M set equal to 0. So 2A tau M plus 4B M cubed plus 6C M to the fifth, that equals 0. Factoring out 2M becomes 2M times the quantity A tau plus 2B M squared plus 3C M to the fourth equals 0. One solution is going to be M equals 0. For non-zero M, we're going to let X equal M squared. So we're going to have A tau plus 2BX plus 3CX squared equals 0. So we're going to get X equals negative B plus square root 4B squared minus 12AC tau over 6C, and M squared equals negative B plus square root B squared minus 3AC, quantity T minus T sub C over 3C. So for T is greater than T sub C, this value is not positive, so M equals 0. And for T is less than T sub C, our M equals plus or minus quantity in brackets, negative B plus square root of B squared minus 3AC times the quantity T minus T sub C in the numerator over 3C in the denominator raised to the 1/2 power. And that near T sub C, we expand the square root, taking this square root of B squared minus 3AC tau. That's approximately equal to B minus 3AC tau over 2B. M squared approximately equal to negative A tau over 2B. So we're going to get M is approximately equal to plus or minus a quantity A times T sub C minus T over 2B raised to the 1/2 power. So that's letter A. Now moving on to letter B. Letter B, they want us to derive the critical component beta. So deriving the critical component beta here, all that's going to be is 1/2. Because critical component, since M is proportional to that square root of T sub C minus T, or T sub C minus T quantity of that to the 1/2, then beta is 1/2. Okay. For part C, I'll read it from the prior page. Part C, suppose an external field H is introduced. Determine the susceptibility. Chi equals the partial derivative of M with respect to H at constant T. So for part C, susceptibility, we include the magnetic field by writing F sub H equals F minus HM, and then H equals this partial F with respect to M equals 2A tau M plus 4B M cubed plus 6C M to the fifth. Our inverse chi equals partial derivative of H with respect to M, and here at T, at constant T, it equals 2A tau plus 12B M squared plus 30 C M to the fourth. And for T is greater than T sub C, M equals 0. So this chi plus equals 1 over 2A quantity T minus T sub C. So for T less than T sub C, near T sub C, M squared is approximately equal to negative A tau over 2B. And then we could say for this chi inverse minus is approximately equal to 2a tau plus 12b times negative a tau over 2b. That equals negative 4a tau. And since tau is less than 0, x minus equals 1 over 4a times the quantity t sub c minus t. And our gamma equals 1. Okay, so that's part C. For part D, under what conditions can the phase transition become first order? So part D, when can the transition become first order? So we could say with A, B, and C greater than 0, the transition is continuous. A first order transition can occur if B is less than 0, C is less than 0. Then the sixth order term stabilizes the free energy while the negative quartic term favors a finite jump in M. At coexistence, one finds M squared equals negative B over 2C, and A, quantity T star minus T sub C equals B squared over 4C. So that T star equals T sub C plus B squared over 4AC for B is less than 0. And the magnetization jumps discontinuously at T star. Some would say T sub star, whichever you prefer. And part E, let's see here. They want us to derive the heat capacity behavior. So for part E, the heat capacity behavior here starts here at the bottom. Heat capacity behavior for T is greater than T sub C, M equals 0, so F sub min equals F sub 0. Ignoring the analytic background contributions, this C plus thing equals 0. For T is less than T sub C, near T sub C, M squared is approximately equal to negative A tau over 2B. Substituting into F minus F naught, that equals A tau M squared plus B M to the fourth. And continuing with this, then we could say, Continuing with this, then we could say F sub min minus F naught equals A tau times the quantity negative A tau over 2B plus B times the quantity A squared tau squared over 4B squared. And then F sub min minus F naught equals negative A squared tau squared over 2B plus A squared tau squared over 4B equals negative A squared tau squared over 4B. So for F sub min, that equals F naught minus A squared times the quantity T minus T sub C squared over 4B. And the heat capacity is C equals T times this second partial derivative F with respect to T. And so since C minus sing equals T A squared over 2B, near T sub C, C minus sing equals A squared T sub C over 2B. So there is a finite heat capacity jump. So this delta C equals C minus minus C plus equals A squared T sub C over 2B. And the critical exponent is alpha equals 0, meaning the heat capacity has a finite discontinuity rather than a power law divergence. Okay, so that's all for this practice problem. Thank you very much and have a great day.